Okay, so let me prove to you that the Rocchio algorithm is a linear classifier and what we mean by a linear classifier. So, um, okay, so let's say you're given, we are going to focus only on two classes. Okay, then we'll see how to extend this to multiple classes, but let's imagine that there are only two classes and we have two centroids. Okay, I'm going to call the centroid for the for this class as the vector C. I'm going to call the centroid for this class as the vector D. Okay, now I have to partition this entire space in such a way that there are two regions. One of the regions has points that are closer to C than to D. The other region has points that are closer to D than to C. So let me pick an arbitrary point in this space. Let me call that as X. By definition, the decision boundary is a, a line or a curve, whatever. I mean, let's not assume that it's going to be a line. Let's say it's a general curve, but it's a series of points. And let's say X is an arbitrary point along that decision boundary. By definition, the distance between X and C is the same as the distance between X and D. Do you agree with me? Right? This is by definition. By the definition of a decision boundary. A decision boundary is a boundary between where points along the boundary are equidistant from either class. Okay. Now let's say X is a vector x1 to xn, C is a vector c1 to cn, and D is a vector d1 to dn. What is the magnitude of the vector x minus c? Well, from simple vector algebra, it's going to be the square root of x1 minus c1 square plus x2 minus c2 square and so on till xn minus cn square, right? For example, if x and if all these are points in a two-dimensional space, then x will be just, it will have an x1 coordinate and an x2 coordinate. So this is just the Euclidean distance formula. Similarly, the magnitude of this vector is the square root of x1 minus d1 squared so on till xn minus dn squared. So you can square both sides here. When you square both sides, you will get x1 minus c1 square plus x2 minus c2 squared so on till xn minus cn squared is x1 minus d1 squared so on till xn minus dn squared. So there are n terms on the left hand side, n terms on the right hand side. So let's open these terms up. So you'll get x1 square minus twice x1 c1 plus c1 squared. And the last term here will be xn squared minus twice xn cn plus cn squared. Simple algebra. x1 square minus twice x1 d1 plus d1 squared. Xn squared minus twice xn dn plus dn squared. So there'll be a lot of cancellation on both sides, as you can see. This x1 square will cancel out with this x1 squared. The next term x2 squared will cancel out with x2 squared. And xn squared will cancel out with xn squared. So the first terms will all cancel out on both sides. Now what are the remaining terms? You'll have minus 2 x1 c1 plus x2 c2 and so on till xn cn plus c1 squared plus c2 squared and so on till cn squared. So let me go to a new page. x1 c1 plus xn cn plus c1 squared is equal to minus twice x1 d1 plus xn dn plus d1 squared plus d2 squared and so on till dn squared. Okay, so I'm going to take this term and move it to the right hand side, and I'm going to take this term and move it to the left hand side. So what do I get on the left hand side? I get c1 squared to cn squared minus d1 squared to dn squared is equal to twice of x1 c1 and so on till xn cn minus x1 d1 minus x2 d2 and so on till minus xn dn. So I can group together these terms. Um, Actually, what is c1 squared plus cn squared? This is nothing but the square of the magnitude of the vector c, right? If you go back to this diagram, so the vector c is nothing but the vector from the origin of the vector space to this point, and the magnitude of that vector is given by the square root of the squares of each of the individual components, sum of the squares of the each of the individual components. Okay, that's by definition that's the magnitude of a vector. I mean, you can prove this also. Basically, the magnitude of this vector is just the length of the distance between the coordinates representing c and the origin, right? And that's going to be given by this formula. So this is actually the square of that distance. This is the square of the magnitude of the vector d. So this is twice of x1 c1 and so on till xn cn is nothing but the dot product of x with the vector c, right? And likewise this is the dot product of x with d. So this can be represented as twice of x dotted with c minus d. Now I can, so basically what we get at the end is x dotted with some constant vector. So note that x is the point that we are varying all across the region, okay? So x will have n parameters, x1 to xn, which are unknowns. These are constants because we know what the centroid of both the classes are. So this will be some set of constants, and this is half of the magnitude of c squared minus magnitude of d squared. So this is actually an integer, right? Because the magnitude of the vector is basically a real number. So actually, sorry, this will be a real number, not an integer. This will be a real number. This will also be a real number because you're taking the dot product of one vector with another vector. So finally, you'll get some scalar value. But the point is that this can be represented. So this has the general form x dotted with, let me call this vector as w, is equal to b, where b is the value of this scalar quantity, whatever that is. So this is the equation of the decision boundary. So this can be represented as x1 times some constant w1, x2 times some constant w2, x3 times some constant w3 times xn times some constant wn is equal to b. Okay, this is the equation. This is the kind of equation that a decision boundary will have for Rocchio. W1 to Wn are constants and b is a constant. Now, going back to your question, what exactly is a hyperplane? Well, suppose we had a two-dimensional plane. Then we would have had only x1 and x2 here because n would have been equal to 2. So in a two-dimensional plane, what is this equation? This is the equation of a straight line. x1 times w1 plus x2 times w2 is equal to p. Okay, b, w1 and w2 are constants. x1 and x2 are the two variables along the two axes. So x1 is like x, x2 is like y. Okay, so this is the equation of a straight line. What if you look at 3 dimensions? So let's say n is equal to 3. Then you would have had x1 w1 plus x2 w2 plus x3 w3 is equal to b. And this, if you note, is the equation of a plane, of a two-dimensional plane. Okay, it's the equation of a two-dimensional plane in 3D space. Just like with n equal to 2, you had the equation of a straight line in two-dimensional space. Now you have the equation of a plane in three-dimensional space. And if you go on increasing the values of n, if you go on increasing the values of n, then you will get higher and higher dimensional hyperplanes. Okay, so hyperplane is a higher dimensional plane. We tend to think of planes as two-dimensional, but you can think of, when we are imagining, you can't imagine a 10,000 dimensional space, but basically, if you had a 10,000 dimensional space, you would have a hyperplane that would divide that space into two regions. Just like you have a plane that divides 3D space into two regions. So you can see that given a test document, how would you classify it using Rocchio? You are classifying it based on whether the test document is located closer to the centroid C or closer to the centroid D. Okay, so when will this test document be closer to the centroid D? Okay, so instead of a decision boundary, if we had to find the equation of, not equation, but if we had to characterize the entire region of points which are closer to C than to D, we would do it in this way. Okay, for any point x in that region, its distance from C is less than its distance from D. So we would work through the same set of equations, except that this equal to would be replaced by a less than sign. And at the end, what do we get? So this would be less than. At the end, we would have got, this would have been less than, this would have been less than, this would have been less than. So putting it the other way, this would have been greater than. So basically, if the test document is going to be closer to the centroid C, if this value is greater than this is greater than B. Okay, because this is x dot w, the right hand side is B, x dot w is greater than B. So all we have to do is we have to find out, given a test document of the form x1 to xn, okay, this is the text document we give, we take a linear combination of the components of this vector. So these weights are something we will calculate in the training phase. We will just multiply the weights that we have calculated with the coordinates of the x of the test document, and we'll see whether the result is greater than B or not. If it's greater than B, then it falls into the class C, otherwise it falls into the class D. So for any linear classifier, okay, let me write this down. For any linear classifier, the test phase is very simple. Okay, compute x dot w and see if it's greater than B or not. Now W and B are something you would have calculated in your training phase. W and B are something you would have calculated in your training phase. So in your test phase, all you need to do is just compute x dot w and see if it's greater than b or not. So for any linear classifier, this is the kind of equation you will get for the decision boundary. I derived this for the Rocchio algorithm, but you can derive this for any algorithm that corresponds to a linear classifier. You will get an equation of this form. So do you now understand what a hyperplane is and what exactly a linear classifier does?
So somewhat, sir, like, so,
Okay, why don't you ask what you didn't understand?
so like, get the part, sir, like x1, w1, x2, w2, but how would it look like a hyperplane?
Well, it's obviously difficult to visualize a hyperplane in say 10,000 dimensions, but a hyperplane is just an extrapolation of a plane to higher dimensions. So what would be the next higher dimension? If you go to 4 dimensions, a hyperplane would be an equation of the form 3x plus 4y plus 6z is equal to 10. Okay, so this would be a hyperplane in 3 dimensions. Now clearly this is a surface. Oh, sorry, this is actually a plane in 3 dimensions. Okay, so just like 3x plus 4y equal to 5, this would be the equation of a straight line. Okay, in 2 dimensional space. This would be the equation of a plane in 3 dimensional space. Do you understand this, or you have problems here also?
Yes, sir. Yes, sir. Got it,
Okay.
sir. Got
Yeah.
this part.
So now imagine going into 4 dimensional space. Then you will have another dimension added to these three. Okay, it could be something like say 8w, and then this will be equal to some constant, let's say 10 only. How would you interpret this geometrically? It's it's a hyperplane. That's all you can say. Hyper standing for the fact that there are more dimensions than we can visualize. Okay, it's a plane
Okay.
in it's a 3 dimensional plane, whatever that means. It's a 3 dimensional hyperplane. So
Okay, sir.
the problem here is in visualizing what a 4 dimensional space looks like, but it's you don't have to visualize or try to visualize. All you have to look at it is that it's a simple extension of a plane to higher dimensions, and this extension is done mathematically rather than visually or geometrically. So it's the formulas are very simple, except that you add more and more terms for higher and higher dimensions.
Yes, sir. Yes, sir.
Okay, so um, if you look at a two-class problem, you can use a linear classifier which will generate a hyperplane that will separate the two classes, or you can use a non-linear classifier which will not generate a hyperplane, but which it will be a much more complicated higher dimensional surface, like we saw in the Voronoi diagram. Okay, so in 2 dimensions we can separate the two classes by a line. In higher dimensions we need, instead of a line, we need planes or hyperplanes. Now one of the things that you can note over here, okay, this is something I also told you. If you have a decision boundary, then depending on which side of the line the test document lies in, you'll classify it into either the red class or the blue class. And that is exactly what I showed you in by deriving that formula. where you'll just check whether a times x plus b times y. So a and b are like w1 and w2, and c is what I called as b in that particular derivation. Okay, so x1 w1 plus y1 plus y times w2. Actually, this may be confusing, but if you go back to that derivation which I showed you, what they are calling as x and y is what I'm calling as x1 and x2. Okay, so I use the notation x1 to xn, and they're just doing it for 2 dimensions, so they are using the notation x and y. But here's an interesting thing you may note. If there is a straight line that can separate cleanly the two classes, then there will actually be an infinite number of straight lines which will separate the two classes, because you can slightly rotate this line and still separate the two classes, right? If this point and this point don't exactly lie along this line, you can imagine rotating this line such that you are still able to separate the two classes. Okay. So what do you think is a better separator? Is it the green line or the black line?
So the green line.
Yeah, why is it the green line?
So because it's so the distances are more between the boundary points. Like
Exactly.
it.
The distances are more, so whereas if you look at this black line, it's possible these 2 points are already so close to this black line that you can imagine there could be another test document which is close to this red point, but which will fall on the other side of this line and get classified into the blue class. Whereas if you look at this green line, its margin, okay, its distance from the red points and from the blue points is larger. The distance of this black line from the red points and blue points is very small. So we say that the margin for the green line is more. The margin is the distance of this line from the closest red point or the closest blue point. It's a measure of that. So we want to maximize the margin. We want to choose a hyperplane that will maximize the margin. Okay. So I think we are out of time. Um, we'll probably continue tomorrow unless you want to stop at this point and go back to any,
So
you know,
uh,